broke Lily's too.
Lily, yeah.
Okay, so when we're talking about why certain reactions happen and why certain things don't happen, that comes down to something called Gibbs free energy. And by free, we mean energy that's not tied up in that entropy. Because remember, entropy is a measure of the energy that's tied up due to this disorder. Okay? It's not available to do any kind of work, and it's tied up with that. So that's where the free energy comes from. And being thermodynamically favorable has to do with, how much energy is there and whether that energy is enough to make the whole thing be able to work. So for example, water does not melt unless it is above 0 degrees Celsius. So it's not thermodynamically favorable for it to melt below 0 degrees Celsius. Okay? It's not thermodynamically favorable for the water to freeze above 0 degrees Celsius, unless you play with the pressures and stuff like that. Anyway. So what we're looking at here is something called Gibbs free energy. And if you look back, if you found that Unit 6 stuff that I referenced yesterday, where we had that table, there was a table that we had delta H values given, we had delta S values given, and we had delta G values given. Okay? So what this tells us is whether these reactions will occur and if they're going to occur at what temperatures they're going to occur. You need to sit down and you need to memorize these columns on this chart. You need to commit these to memory. Sometimes just looking at the arrows here helps. These are in alphabetical order. These arrows, okay? And think about this. This is kind of like a hug, right? If you look at that, okay? That's all temperatures. It's bringing everything in, like if somebody was to hug you, okay? Here, it's excluding everything. It's not going to happen at any temperature. So sometimes looking at the symbols helps you remember what this has to be and this. Does that make sense? And this is at high temperatures. This is going to be at low. So you just got to kind of work that out in your mind, what those mean. Okay? So like I was saying, the Gibbs free energy is the energy available in a system that can do work. By calculating the Gibbs free energy, we can determine if the system has enough energy to undergo the process and is therefore thermodynamically favorable. Again, we don't want to really use this term spontaneous because that tends to kind of muck up the works. People think that the thing is going to happen. Boom, it happened. Okay? And a lot of times those spontaneous or thermodynamically favorable reactions take a long time, like the rust on my bumper on my truck, or side panels or whatever.
Is it actually rusting?
Yeah, you want to go out and look at it sometime?
Yeah.
Come on.
I do.
It's like 12 years old. Yeah, she's starting to rust.
My car is rusting.
Okay.
That's sad.
As we've seen before, there's two factors at work. We've got enthalpy, which is heat, and we have entropy, which is that measure of those microstates. What determines if the reaction will take place is we have to look at both of these factors. If a reaction is thermodynamically favorable, we know that it will take place. However, it does not tell us how fast that reaction will take. For example, some thermodynamically favorable reactions are very slow, like rust. This is an example of a reaction that is said to be under kinetic control. We have to look at the kinetics, which was unit 5, I believe.
Yeah, it was.
to determine the rate of that reaction. So we did unit 5, we talked about rates of reactions. Remember the first order, second order reactions? Okay. So enthalpy is going to describe the energy required or released in a chemical reaction. We know that exothermic processes are ones that release energy. Those tend to be favored. So delta H, when delta H is negative, we tend to have that's like, all kind of reactions tend to go to that order. Entropy then is the amount of energy as a function of temperature that is not available for work because it's lost to that molecular disorder. We know from the second law of thermodynamics that an isolated system, a sample will arrive at a state of thermodynamic equilibrium where entropy is highest. So things tend to go to more microstates or more disorder, just like my desk. Processes that move to greater entropy are favored. So things that release heat and things that go to disorder are favored. So negative delta H, positive delta S. In some cases, it's necessary to consider both the enthalpy and the entropy to determine if the process will be favored. Like I said, freezing water at standard pressure. When water freezes, it's going to release energy. The particles have more order in the solid form than they did in the liquid form. So the delta S is negative. We know that when temperature is less than 0, it will spontaneously freeze. So delta G is negative. But if the temperature is over 0, it won't freeze. Your delta G will end up being positive. Delta G is Gibbs free energy. And delta G, if it is negative, then it's thermodynamically favorable. If it's positive, then it's not. We can also look at sodium nitrate when we put that in water. It's a nitrate. So what do we know about that? And it's sodium. What do we know about sodium and nitrate when they're placed in water? They're soluble, right? It's a snap. Remember ammonium and potassium. Good. Okay. All right. So endothermic process, through the dissolution of this is an endothermic process, the thing will actually feel cold to your hand. The heat is absorbed from the water, so the delta H is going to be positive, which tends to be unfavorable. However, the ions become more disordered when they're dissolved, so the entropy is going to increase. And we know that this is going to happen because it's a snap, so delta G has to be negative. So here your entropy is going to drive this reaction. So these two examples, there's several factors at play here. We have entropy. Okay, we learned how to calculate that yesterday in 9.2. We also have delta H. We learned how to calculate that back in unit 6, I believe. And we have temperature. Temperature has to be in Kelvin. So if it's in Celsius, what do you got to do? 273, right? Okay. So if your, so this is our equation for Gibbs free energy. Okay. And this is on your AP exam formula sheet. Okay. If delta G is less than 0, then it is thermodynamically favorable. Like I said, check your units. Because typically, and I talked about this yesterday, typically your entropy is going to be in joules per mole Kelvin, while your delta H is going to be in kilojoules per mole. So you're going to have to convert your joules into kilojoules. So if we had 372 joules per mole Kelvin, how would I get that to kilojoules? Yep, I'm going to move the decimal place 3 places to right there. Okay, and then also notice that this entropy has Kelvin in it. So that's why if the temperature is given in Celsius, I've got to convert it to Kelvin in order for it to work and cancel out my units. That makes sense? All right. So we know that temperature increases when entropy of the system increases. So as an increase in temperature, that would also magnify your entropy. So that's why they multiply those together. We subtract this term from the enthalpy, and that gives us the energy available to do work. So here's your total energy, but we have to subtract out that part that's lost to that disorder because it's not available to do any work. And if we end up with a positive delta G out of this, then that means that we're not going to be thermodynamically favorable. It has to be a negative delta G in order for it to work. So again, you need to memorize this chart. Memorize this. Or be able to rationally understand how these things work. Oh, they put it on here twice because it's kind of important. Libby hasn't told you to memorize a whole lot this year, but this is one you got to commit. Well, SNAP is not hard to remember. I mean, yeah, but the strong bases are easy. All you do is just on the periodic table. I mean, that's not hard. The bond, yeah, but I told you about that back. Like you knew that last year. So. Oil rig isn't hard to remember.
What's the other one?
And you're going to add fat cat to that oil rig.
Wait, what's the other one? Oil rig? Wait, is there two?
Oxidation is loss, reduction is gain. Yeah, there. Some people use oil rigs. Some people use Leo goes Gur. All right, so we can calculate our entropy then when we have our reactants. This is in a standard state. Standard state refers to the substances. It's going to measure gases at 1 atm of pressure. Solutions are going to be in 1 mole. Temperatures at 298. And they tell you that it's that way when they have this little circle here. This little circle means prime. That means that you're at standard conditions. Standard conditions are different from STP. STP, if you remember, is standard measurements are at are at STP. Your temperature is 273. It's not. These are standard state conditions. So that's different from STP. You learned STP when we talked about gases. Good. All right. So we have decomposition here of hydrogen peroxide. It's going to occur slowly at room temperature according to the following reaction. What would the delta G sign for this be? Positive or negative? Negative, because it's going to occur on its own. We're not doing anything to it. Okay? Delta S. Positive, yes. Because it's going from 2 moles to 3 moles, and it's going from a liquid state to a gaseous state. So there's a couple of different reasons there that that happens. All right. Value for delta G here. All right, so we've got to figure out our values here. So we've got our delta G. We've got to figure that out for our products. And then subtract the delta G values from our reactants. So we're going to figure out our products first. So we have 2H2O. So that's 2 times negative 237.2. I've got 4 times negative 394.4. And my nitrogen is 0. All right. And then for my product side here, I have 4 times 121. So that's going to be 484. My bad. Sorry. Oh, shoot. Can I just Control Z that all the way? Yeah. 4. Good grief. Come on, Lippy. 484. Okay. So now I need to take my products minus my reactants. So I'm going to have negative 2052 minus 484. That's going to give me a negative 2534. And that's going to be kilojoules per mole. And they wanted to know if it was going to be thermodynamically favorable. Yes. Why? Right. My delta G value is negative, therefore it's thermodynamically favorable.
Calculate each side and then subtract the reactants from the products.
Mm-hmm. Yep. And that's on your formula sheet too. This equation here. Let's see here. This guy right here is on your equation sheet. That's one that we just used. Okay. All right. Questions on that? All right. So let's look at 9.4, thermodynamic and kinetic control here. Again, if the value for Gibbs free energy is negative, then that means that the reaction is thermodynamically favorable. Not all reactions that are thermodynamically favorable actually occur, though. For example, the reaction of carbon diamond to carbon graphite is thermodynamically favorable at room temperature. However, we don't see diamonds turning into graphite over the course of a lifetime. So I don't have to worry about my ring changing into pencil lead.
Oh my God. That would be horrible.
Okay? A lot of people would lose a lot of money.
How long does it take?
Oh, it's a long time. It would have to, so for carbon as a diamond, which is here, this is a covalent network solid. It's going to form a macro covalent network solid for carbon as a diamond to turn into graphite, which is here, okay, where we've got sheets. Every time you write, you're sloughing off a sheet of carbon. Okay, that's how it works. That's how your pencils work. Okay, it would have to break those bonds, these bonds in between here. It's going to have to break those bonds in order to have this happen. Okay, to do that, you have to have such a stupid amount of activation energy that it's really not going to take place. So this is a classic example of a reaction that is thermodynamically favorable, yet the kinetics of the reaction prohibit it. It's got to have so much activation energy that it's never going to happen. So we describe reactions like this as being under kinetic control, which means that the kinetics of the reaction determine if it's thermodynamically favorable and whether it will occur. So generally, if the thermodynamics, your delta G predicts, so you have a negative delta G, and it predicts that a reaction will take place, but the reaction doesn't happen, we assume that it's under kinetic control. So if you do a calculation and you come up with a negative delta G and they say, but the reaction still doesn't occur, your answer should, and they ask you why, you should react with, it is under kinetic control. Factors that would influence this would be high activation energies, unfavorable orientations. Remember, in order for certain reactions to happen, you have to get certain things to smack together in the right orientation. We talked about that in terms of, like, you know, a cap on a pen or something. You have to make sure that it's oriented right, or else you're never going to get that cap on there. If I go like this all day long, that cap's never going to get on that pen. Okay, they have to come together to be able to click together and collide the right directions. Remember, we talked about that back in the day. Or you need a high number of particles to collide at the same time. So when we talked about those orders of reactions, if you had like 5 things that had to come together in this right orientation at the same time, the likelihood of that happening was not great. Okay. All right. So consider this. What do you see as your sign for delta S here? Delta S represents what? Entropy. So is our entropy increasing or decreasing? Okay, so our delta S would be positive. Yep. What about our delta H? What about our delta H?
Negative. Positive. Negative. Negative.
Exothermic. It's exiting these bonds. It's leaving. All right. Here's your first foray into that chart. Remember we talked about the chart over here? So you got a positive delta S, you've got a negative delta H. Delta H is less than 0 and delta S is greater than 0. That's why it's a positive and a negative. So what did that tell us it should be? All temperatures. So it will always happen. This reaction does not proceed at room temperature. Can you suggest a change to the conditions that make the reaction proceed? Okay, so we could increase the temperature to give the reactants more energy. So we could increase temp to give more energy. There's one other way. You said activation energy, right? So that means that this is too high. How could we lower this? Catalyst, right. Now, can you suggest a change? On the AP exam, if they ask for a change, you do not write both of these down. Both of them are correct, only write one down. It doesn't matter which one, but you only write one. Why? No, they won't take off a point. Well, they'll take off a point if you're wrong.
Because you can't do both.
Okay, no, you could do both.
Because if you get one wrong.
If you get one wrong, they're going to make both of them wrong. And they asked for one change. This is a timed exam. Do not spend time trying to show them how smart you are. You do not have time to do that. They know you're smart. You took AP Chem. Okay? You write one thing down and you move on because you don't have time. Fair enough? Okay. Now, we're going to consider the reverse reaction. What would our sign for delta S be?
Less.
Minus, yep, negative. Our delta H would be positive. We reverse the reaction. So what do you think is going to happen to these symbols, folks?
I was thinking about this. I was thinking about.
It's a Friday, so.
All right, when will delta G be negative? Never.
Oh my God.
Reaction doesn't proceed at room temp. Well, duh. Can you suggest a change to the conditions that make the reaction proceed? At room temperature.
Oh no, that's so disgusting.
No.
My blister just popped.
There are Band-Aids in the top drawer if you need one.
I burnt my hand on hot glue gun and it just exploded.
Wait, why not?
You can't make it happen.
No way.
Not at room temperature. You could, we're going to find out that there's a way to make these reactions happen, but you have to input extra energy in, like in the form of electricity or something like that. Mm-hmm. Change of the conditions. So we're going to talk about electrolysis and that sort of thing coming up, but not right now. All right, we got this reaction here. They gave us the delta H, they gave us a delta S, and they want us to calculate delta G. So delta G is going to equal delta H minus delta S, and I think temperature is listed first. It doesn't matter because you're multiplying it together. This is the equation we're going to use. Again, check your units here. Okay, this is in kilojoules. This is in joules. So I need to take and I need to move my decimal point 3 spots over. I also need to verify that my temperature is in Kelvin. If this is not in Kelvin and this is in Kelvin, you have to convert this over. All right, so this is going to equal a negative 1648 minus 298 times negative 0.544. So multiply these together and then subtract that value from this value to come up with your answer. And when you do that, you should end up with negative 1,485,89. And what are my units? Well, we got to figure that out. Okay. This was kilojoules per mole. Okay. This was Kelvin, and this was kilojoules per mole Kelvin. So this Kelvin and this Kelvin are going to cancel out. And then that'll allow you to do your subtraction with your kilojoules per mole. This reaction is very slow at room temperature, but is much faster as you add water to the reaction. Why? Why would it be slow?
Because there's a solid.
Okay. But remember what's going to slow things down. What? Yeah, but what did we say up here was going to be a cause of things being slow? Okay, so maybe the orientations aren't correct. Yep, but it's under kinetic control is what you're going to say. Okay, so it's slow due to it being under kinetic control. When we added the water to the reaction, what happened there? Well, adding the water provides an alternate path which lowers the activation energy. All right, they wanted us to sketch an energy diagram showing both circumstances described in part B. We know that it is an exothermic reaction, so it's going to start here. It's going to go up, and it's going to be exothermic, so our products are going to be less energy than, so this would be our no water. And then if we drew that with an alternate path with water, it might look something like this, okay? Since it lowered the activation energy. What happens to the value of delta G when the water is added? Nope. Doesn't get lower. Stays the same, right? We didn't alter our delta H at all here. We didn't alter our temperature. So this is just going to stay the same. Okay. They didn't say that it dissolved. They just said that we added water. Okay. So only the kinetics changed here. Okay. So this weekend, I want 9.3 and 9.4 done. And I did upload the answer keys. It's not a terrible lot, so hopefully you'll be able to get that done. Okay.